This video illustrates a model of uncertain insurance claims. The insurance company has three types of claims: automobile, general liability, and workers' comp. It wants to estimate the distribution of next year's total claim amounts in each of these categories, as well as the total over all categories. To do this, it must estimate the number of claims of each type and the typical claim amount of each type. The company has the historical claim data shown here. The upper section lists the number of claims of each type for the past 20 years. Several summary measures appear to the right of the data. For example, each year had between 839 and 1219 auto claims. Based on only 20 data points for each claim category, it is difficult to find an accurate estimate of the distribution of the number of claims in a given year, so the model will assume that the number of claims for each type in the next year is uniformly distributed between the minimum and maximum values observed for that type. Also, because the correlations across categories are fairly small, the model will assume that the numbers of claims in the different categories are probabilistically independent. I will now enter these uniform, or actually integer-valued uniform distributions in the model sheet. The bottom section of the historical data sheet lists the previous year's claim amounts for each of the three categories. For example, there were 845 auto claims in the previous year, so the first column contains $845 values. Now there are plenty of data points, so it is possible to estimate the distribution of claim amounts for each category. This can be done with At-Risk's distribution fitting tool. Although many distributions could be fit to the data in each column, the triangular distribution is a reasonable choice. In fact, the defined data sets for the three categories have already been set up. For example, here is the triangular fit to the auto claims. It is clearly a very good fit. I can now enter this fitted distribution into the model sheet. And then I can proceed similarly for the general liability and workers' comp categories. Summing up the results based on historical data, the number of claims in each category is assumed to have an integer-valued uniform distribution, and a typical claim amount for a given category is assumed to have a triangular distribution fitted to the data. The challenge now is to find the total of all claim amounts in each category. Logically, this should be a sum of random claim amounts, where the sum has a random number of claims. However, it would not be correct, for example, to multiply the number in C4 by the number in cell C5, because this would assume that all auto claim amounts are the same random amount. For example, with the values shown here, it would assume that each of the 1029 auto claims had an amount 3547. In reality, this underestimates the amount of uncertainty, because these auto claims are not the same. They vary from claim to claim. Fortunately, At-Risk has a special function created exactly for this type of situation, a sum of random amounts with a random number of terms in the sum. It is the risk compound function, which has two arguments. The first argument is the number of terms in the sum, and the second argument is the distribution of a typical term in the sum. On each iteration of the simulation, At-Risk uses this function to generate the number of claims in row 4, and then it generates this number of claim amounts, each a random draw from the distribution in row 5, and it sums them. Actually, this same function would work even if the values in row 4 were fixed numbers, but risk compound is usually used when both arguments are random. Now it is easy to complete the model. A risk compound function is entered in each category of claim in row 9. They are summed in cell F9, and all of the cells in row 9 are designated as at-risk output cells. Finally, summary statistics can be entered in the bottom rows. Of course, these won't be meaningful until the simulation is run. Now I will run the simulation with 1,000 iterations. Here is the distribution of the total amount of auto claims. You might expect the sum of random amounts to have a bell-shaped normal distribution because of the central limit theorem. But this theorem doesn't apply when the number of terms in the sum is random, as it is here. The distribution you see is almost uniform, with very short tails. In contrast, here is the distribution of the grand total. It is the sum of the 3 distributions to its left, all of which are at least symmetric and somewhat bell-shaped. Therefore, because of the central limit theorem, the distribution of this sum is approximately normal. Now the company has a reasonably good idea of its total exposure in the coming year. For example, it sees that there is a 5% chance that the total of all claims will be less than about $9.72 million, and perhaps more importantly, it sees that there is a 95% chance that the total of all claims will be no more than about $15.44 million.